All right, here are solutions to perfect problem 1 from Math 111. One little note here. This problem gets really difficult because we have different bases for our exponents. So I want to give you a way to be able to convert between things that are base 2 and base 10. We'll later learn ways to do that using logarithms and some other tricks. But for now, we don't have any, so I just wanted to make this note that 2 to the 10th power is very close to 10 cubed. In fact, it's so close that for our purposes, we can just assume they're the same thing. All the work will work out fine. These are spread out enough that making that tiny little assumption won't change any of our answers. So we're going to assume that 2 to the 10th power is 10 cubed, even though they're not really the same. If you make that assumption, we can rewrite these guys. For example, 2 to the 100th power. If for some reason we wanted that as base 10, like maybe we want to compare it to part f here, which is 10 to the 80th power, we could say that this is 2 to the 10th power to the 10th power, because we have that exponent rule that says when you're raising an exponent to another exponent, you multiply them. So this is 2 to the 100th. But we just said assume 2 to the 10th is the same as 10 cubed. So that thing inside the parentheses, instead of writing 2 to the 10th, you could write 10 cubed. And 10 cubed to the 10th power, again, we apply that rule where when raising exponents to exponents, you multiply them. We could say part A is the same as 10 to the 30th power. Really, there shouldn't be an equal sign. There should be an approximately equals to sign here. But for our purposes, I said we can just assume they're the same. So now we have A both as base 2 and base 10, which will be helpful. B, 100 to the 10th times 100 to the 10th. Well, one rule we have is that when you have the exact same base, you can add the exponents. So 10 plus 10 is 20. This is the same as 100 to the 20th power. But 100 is 10 squared. Right, 100 is 10 squared, so instead of 100 to the 20th, 10 squared to the 20th. You can now apply that rule that when you're raising exponents to exponents, you multiply them. So we get that part B is really 10 to the 40th power. C, all right, we got 4 cubed to the 4th power to the 5th power. Applying that rule twice where you can multiply exponents, 3 times 4 is 12 times 5 is 60. We get that this is 4 to the 60th power. But we don't really want anything base 4. 4 is the same as 2 squared. So I can say this is 2 squared to the 60th power, or 2 to the 120th power, which already would compare with A, but it wouldn't let me really compare it with B. So maybe what I'll do is I'll change this into base 10. I could say this is 2 to the 10th power raised up to the 12th power, because 10 times 12 is 120. And as we said above, we can assume that 2 to the 10th is the same as 10 cubed. So by this long chain of logic, we can call this thing 10 to the 36th power. This mess, we have the same, everywhere inside the parentheses we have the same base, so we can just add the exponents. I don't really want to copy that whole thing, but if you add up 1 plus 2 plus 3, 4, 5, 6, 7, 8, 9, you end up with 45. So really this thing is 2 to the 45th power squared. Don't forget you got this squared out here. Multiply those exponents, you get 2 to the 90th power using the same tricks we've been doing. That's 2 to the 10th to the 9th, which we're going to assume is the same as 10 cubed to the 9th. In other words, 10 to the 27th. Now that we have it as base 10, I guess we can compare it with the rest of these guys. All look right. 2 to the 45, 2 to the 90th, to the 10th, cubed. All right, I think we're good there. E. E's kind of a mess. I guess they're all kind of a mess. But if you apply that rule where you can multiply exponents together, 2 times 2 is 4, times 2 is 8, 16, 32, 64, 128. This is really 2 to the 128th power times 5 to the 128th power, multiplying all these 2's. And we have a separate rule that says if you have different bases, but you have the same exponent, you can multiply those 2 bases together. So what we end up with here is 10 to the 128th power. by far the largest that we've seen. The nice thing about f is it's already written as 10 to the 80th power for us, nothing we need to do. So now we can order these things. So let's see, d is the least, right? 10 to the 27th is the smallest here. That thing is less than a, which is 30th. 10 to the 36th is next. 10 to the 40th comes after that. Let's see, f would be next. And then finally e. So there you go. There, e, this weird thing, was actually a number bigger than the number of atoms in the universe. This thing's pretty big. They're all pretty big, to be perfectly honest. 10 to the 27th, that means a 1 with 27 zeros after it. It's a huge number, but not nearly as big as this number, for example. But that's final answer, and I guess that's the end of the solution.